Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Right now, in the constellation of Virgo, there is a dead star that is actively eating the shattered remains of a rocky planet.
Yep, literally right now.
Right. And a planet that, if you look at the chemistry, looks almost exactly like Earth.
Down to the core elements, yeah.
And the really crazy part is the only reason we even know this is happening is because a billion-dollar machine sitting on a mountain in Arizona was, well, it was having a bad weather day.
Just a cloudy night.
A cloudy night. So I want you to imagine for a second that you could look into a cosmic crystal ball. But, not one that tells your fortune.
Right. No magic here.
Exactly. This is a lens looking deep into our local galactic neighborhood, and it's revealing the ultimate, chaotic, and frankly, terrifying fate of our very own solar system.
It is deeply terrifying when you really think about it.
It is. We are talking about white dwarfs actively cannibalizing their own planetary systems, and the accidental scientific breakthrough that just gave us a front row seat to the destruction. Okay, let's unpack this.
I mean, it is just a phenomenal starting point. Because, we really have to reorient how we think about the cosmos.
How so?
Well, when you look up at the night sky, it feels completely static, right? Like, the constellations don't change.
Yeah, Orion is always Orion.
Exactly. But this discovery reminds us that stellar neighborhoods are incredibly dynamic, violently kinetic environments, especially at the end of a star's life cycle.
Right.
To really understand the planetary wreckage we're seeing, you have to understand the specific physics of the engine that's driving the destruction. And that is the white dwarf itself.
Okay, I want to stop you right there because I was reading through the underlying physics of this, and calling it a dead star feels like a massive undersell.
Oh, totally. It's a misnomer, really.
Yeah, because we all know a white dwarf is the leftover core of a star, like our sun, after it runs out of fuel and sheds its outer layers. But it isn't just a burnt-out piece of charcoal floating in a void.
No, not at all.
It's an object held up entirely by, quantum mechanical forces, right?
Yeah, you're touching on electron degeneracy pressure.
Which sounds like something out of Star Trek.
It does. But
yeah,
it's real physics. So when a main sequence star exhausts its hydrogen and helium, nuclear fusion just stops.
The fire goes out.
Right. And the outward pressure that was holding the star up against its own gravity, it just vanishes.
The gravity just completely takes over.
Exactly. The core collapses inward, and it keeps collapsing until the laws of quantum mechanics literally forbid the matter from squeezing any tighter.
Because things can only get so dense.
Right. It's a rule that two electrons cannot occupy the same quantum state. So the collapse finally halts, leaving this sphere composed almost entirely of carbon and oxygen.
And it's coated in a thin layer of helium, right?
Yeah, and usually a tiny veneer of hydrogen on the very top.
And the sheer density of that sphere is where the mechanics of this whole, planetary cannibalism begin.
The density is the critical factor. You have to imagine taking a mass roughly equivalent to the sun.
Which is huge.
Huge. About 330,000 times the mass of the Earth. And you are compressing it down into a sphere the exact size of the Earth.
That is just, I can't even wrap my head around that math.
It's mind-boggling.
Yeah.
The surface gravity of a white dwarf is roughly 100,000 times stronger than what you're experiencing, just sitting in your chair right now.
Wait, really? 100,000 times?
Yes. A single teaspoon of white dwarf material would weigh something on the order of 5 to 10 tons.
A teaspoon.
One little teaspoon.
Okay, so we have this ultra-dense Earth-sized gravity well, but here is the part of the orbital dynamics that really tripped me up.
Wait, lay on me.
So you have a solar system with rocky planets, gas giants, asteroid belts, and the star dies.
Right.
Now, the star loses a massive amount of its mass when it puffs off those outer layers, right? Like as a planetary nebula.
Exactly.
So if the central star loses, say, half its mass, shouldn't the gravitational grip on everything weaken?
You would think so, yes.
By the laws of physics, wouldn't the planets just drift outward into wider, safer orbits? Why are they suddenly plunging inward just to get eaten?
What's fascinating here is how that exact mass loss triggers utter chaos.
Chaos.
Pure chaos. You are completely correct that adiabatic mass loss causes orbits to expand. The planets do drift outward.
Okay, so I'm not crazy.
No, you're spot on. But they don't do it uniformly. You have to view a solar system not as a set of isolated rings,
Okay.
but as a complex, interconnected gravitational web.
Like an N-body system.
Precisely. When the central anchor loses mass, the distances between all the planets change, which means their gravitational influence on one another changes drastically.
Because Jupiter isn't just orbiting the sun, right? Jupiter is also pulling on Mars and Earth and the asteroid belt.
Yes, that is precisely the point. So when those orbits expand, the system often crosses these critical thresholds called secular resonances.
Secular resonances.
Right. The massive gas giants, the Jupiters and Saturns of that specific system, find themselves in slightly unstable orbital configuration.
They get wobbly.
Yeah, their orbits might become highly eccentric, meaning elliptical rather than perfectly circular.
Okay.
And as these giant planets sweep through their new elongated paths, their immense gravity acts as a massive perturbation force on the smaller, rocky bodies in the inner system.
I see. So it's like a cosmic blender or like a chaotic game of stellar billiards.
That's a great way to put it. Or, think of it like a spinning figure skater pulling their arms in and out.
Oh, yeah.
But imagine they're surrounded by other skaters trying to hold on to their hands.
That sounds dangerous.
Exactly. The momentum shifts are violent. The gas giants end up slingshotting asteroids, moons, and even entirely intact rocky planets.
Wow.
Many just get ejected from the system entirely. They become rogue planets.
Just floating in the dark.
Yeah.
Yeah.
But a significant fraction are scattered inward. They get sent on these highly eccentric trajectories that dive dangerously close to the white dwarf.
Okay, so a rocky planet is hurled inward. But from what I understand, it doesn't just hit the white dwarf like, a meteorite hitting a desert.
No.
The destruction happens before it even touches the surface, thanks to the Roche limit. Break down the actual shearing force of that for me, because it sounds intense.
It is incredibly violent.
Mm-mm.
The Roche limit is the distance at which the tidal forces of the central body, the star, exceed the internal gravitational self-attraction of the approaching body.
The planet.
Right. Because the white dwarf's gravity is so insanely strong, the gravitational pull on the side of the planet facing the star is significantly stronger than the pull on the far side of the planet.
Ah, it's the inverse square law in action.
Exactly.
The closer you get, the gravity doesn't just increase, it spikes exponentially.
Yes. So imagine a solid rocky planet approaching the white dwarf.
Okay.
The star is pulling the planet's front hemisphere so much harder than its back hemisphere that the planet is physically stretched.
Like taffy.
Yeah, like planetary taffy. Initially, the chemical bonds of the rock and the internal gravity of the planet resist.
They try to hold it together.
Right. But as it crosses the Roche limit, that differential pull exceeds the tensile strength of silicate rock and iron.
Oh, wow.
The planet doesn't just crack, it undergoes catastrophic mechanical disintegration.
That is deeply unsettling.
It really is.
You have an entire world, a mantle, a core, maybe a crust with a complex geological history,
Gone.
just sheared apart in a matter of hours or days.
It's completely pulverized. It breaks into smaller and smaller fragments until it forms this massive swirling accretion disk of dust, gas, and pulverized rock.
just orbiting the dead star.
Exactly. And over time, through collisions within that disk and something called radiation drag, that planetary material loses orbital momentum, and it literally rains down onto the surface of the white dwarf.
Which sets up the core observational puzzle of this entire field, right?
Yes, it does.
Because if this planetary debris falls onto the surface of a star that is essentially a blindingly hot nuclear ember,
Right.
how on earth do we actually see it? It's literally falling into a stellar furnace. Doesn't it just vaporize and blend in?
This is where we rely on the specific chemistry of a white dwarf's atmosphere.
Okay.
And it's a phenomenon astronomers call stellar pollution.
Stellar pollution.
Right. Remember, a white dwarf's outer atmosphere is pristine.
Because of the gravity you mentioned.
Exactly. Because the gravity is so extreme, the elements stratify almost perfectly by weight.
Oh, I see.
The heaviest elements sink straight down, leaving only the absolute lightest elements floating on the surface. Usually just hydrogen, and in some cases, helium.
Got it. So it's a perfectly clean canvas.
Right. And here is where we have to address a bit of a quirk in the astrophysics vocabulary.
Oh, boy.
Yeah. To an astronomer, any element on the periodic table heavier than helium is classified as a metal.
Okay, I have to push back on this.
I knew you would.
Because it drives anyone who took a high school chemistry class completely insane.
It's true.
Calling oxygen or carbon a metal makes zero structural sense. Why do astrophysicists refuse to update their terminology?
It is entirely a historical hangover from the early 20th century.
Really, just stubbornness.
Pretty much. When pioneers like Cecilia Payne-Gaposchkin were first deciphering stellar spectra, they realized stars were like 98% hydrogen and helium.
Right.
Everything else was just a trace impurity. So for the sake of simplicity in their mathematical models, astronomers lumped all those heavier elements into a single variable.
It's to catch all.
Exactly. Usually denoted by the letter Z. And they just called them metals.
And it's stuck.
It's stuck. So today, when an astrophysicist looks at oxygen, silicon, or magnesium falling into a star, they call it metal pollution.
Okay, well, I'll accept the historical context, even if the chemists listening are currently crying.
Apologies to the chemists.
So we have this shredded planet, which is full of heavy metals, air quotes, like oxygen, iron, and silicon.
Right.
And it's raining down onto this pristine hydrogen atmosphere of the white dwarf.
And that rain fundamentally alters the light the star emits.
Because of spectroscopy.
Exactly. We use spectroscopy to look at the star. Different elements absorb very specific wavelengths of light.
So when the light from the white dwarf passes through this newly polluted atmosphere,
the heavy elements absorb certain colors, and it leaves dark gaps absorption lines in the spectrum.
Oh, wow.
We can read those lines like a chemical barcode.
It's like finding a single breadcrumb on a perfectly clean kitchen counter.
Yes.
It tells you exactly what kind of sandwich was just made.
That is a perfect analogy. But here is the critical temporal mechanic of this.
Okay.
Finding those elements isn't like finding a permanent scar on the star.
Wait, really?
Yeah. I mean, because of that sinking process we talked about earlier.
Ah, right. I was reading about the sinking timescales, and it completely changed the context of what we are observing.
Exactly. Because of that 100 to 501 surface gravity, heavy elements do not linger.
They just drop.
In a hydrogen-dominated white dwarf atmosphere, elements like iron or calcium will sink out of sight beneath the surface layer in a matter of days or weeks.
Days.
Just days.
Huh.
Even in helium-dominated atmospheres, where the convection zones are a bit deeper, they might only last 1 million years.
Which is a blink of an eye on a cosmic timescale.
A total blink of an eye.
It's like dropping a bowling ball into a swimming pool.
Oh, I like that.
Like, if you walk by the pool and see the bowling ball floating just beneath the surface, you know someone must have dropped it in exactly a millisecond ago.
Yes.
Because otherwise gravity would have already pulled it straight to the bottom.
That is a brilliant way to conceptualize it. The sinking timescale is the key to this entire field of study.
Because it means it's happening right now.
Exactly. If we point a telescope at a white dwarf and see the spectral lines of calcium or magnesium, it means the star is actively accreting a planet right now.
The debris is currently falling.
Yes.
Yeah.
We are not looking at planetary destruction that happened 1 billion years ago. We are watching a live feed of the autopsy.
That gives me chills. And the sheer volume of this happening is what really caught my attention.
The numbers are staggering.
Right. This isn't some incredibly rare 1 in a million freak occurrence. When astronomers conduct surveys of the hundreds of thousands of known white dwarfs, between 20% and 50% of them show this active metal pollution.
Just let that number sink in for a second.
Right.
Up to half of all white dwarfs are currently eating the remnants of their solar systems.
Half.
It tells us that rocky planetary systems are ubiquitous in our galaxy.
Right.
And that this violent, chaotic scattering is a standard, totally inevitable phase of stellar evolution.
But wait, if up to half of them are polluted, why don't we have an encyclopedic knowledge of thousands of destroyed exoplanets?
Oh, the catch.
Because we know over 1,750 white dwarfs are actively accreting right now. But the data we actually use to understand exoplanet geology relies on just a tiny fraction of that number.
Wait.
Why is there such a massive bottleneck in getting good data?
It is entirely a limitation of our instruments and, honestly, the physical reality of white dwarfs.
Because they're small.
They are incredibly tiny. They have the surface area of the Earth, not the sun. Consequently, they are incredibly faint.
Oh, so they're just hard to see.
Exactly. To get a high-resolution spectrum where you can clearly separate the faint absorption line of calcium from the background noise of the universe, you need a massive telescope.
Just staring at it.
Staring at that faint pinpoint of light for a very long time. It requires an incredibly high signal-to-noise ratio.
Right.
For the vast majority of those 1,750 polluted white dwarfs, the data is just too noisy.
Too fuzzy to read.
Exactly. It's too noisy to definitively state the exact chemical makeup of the planet being eaten.
Which perfectly sets the stage for the DSI project.
Oh, yes.
And honestly, the sheer serendipity of how this specific data was gathered. Because here's where it gets really interesting.
It's such a great story.
The scientists who captured the clearest look we've ever had at these shattered worlds weren't even supposed to be looking at them.
It is one of my favorite recent examples of scientific resourcefulness.
Tell us about it.
So, to appreciate it, you have to understand the primary mission of the instrument involved. We are talking about the Dark Energy Spectroscopic Instrument, DAE, mounted on the Mayall 4-meter telescope at the Kitt Peak National Observatory in the Arizona desert.
So this is an instrument built to map the expansion of the universe.
Correct.
We are talking about cosmology on the grandest scale imaginable.
Right. DSI's primary 5-year mission is to capture the spectra of tens of millions of distant galaxies and quasars.
Tens of millions.
It's massive. It uses 5,000 robotic fiber optic positioners to look at 5,000 different galaxies simultaneously.
That is insane.
It's an engineering marvel. Not even just clouds. Turbulence. To see a distant, diffuse galaxy, the atmospheric turbulence must be incredibly low. Astronomers call this seeing.
Oh, right. Like good seeing or bad seeing.
Exactly. When the seeing is poor, the atmosphere boils and shifts the incoming light. It turns a faint galaxy into an unreadable, blurry smear on the detector.
So you have nights in Arizona where the seeing is bad.
Yes.
The atmosphere is turbulent. DESI cannot execute its primary mission of mapping dark energy. But telescope time is fiercely competitive, right?
Oh, incredible.
You don't just put the lens cap on and go grab a coffee.
Absolutely not. Every minute of a 4-meter class telescope is scheduled and budgeted.
So what did they do?
This is where a team led by Paul Isconcerto at the University of Warwick executed a brilliant pivot.
Okay.
They realized that while atmospheric turbulence destroys the data for faint, diffuse, extended objects like galaxies, it is far less destructive to the data from point sources.
Point sources, like stars within our own Milky Way.
Exactly. A white dwarf is a point source. It's relatively close, and its light is concentrated into a single sharp pinpoint.
So it pierces through the bad seeing a bit better.
Right. Even if the atmosphere smears it a little bit, all the light is still going right down the fiber optic cable into the spectrograph.
That's brilliant.
So Paul Isconcerto's team proposed a side project.
A side project on a billion-dollar telescope.
Just a little side hustle. During those windows of suboptimal weather, when DSI's eye couldn't look at the edge of the universe, they would repurpose the 5,000 robotic eyes to look at white dwarfs right here in our own galactic backyard.
It's an incredible hack.
It really is.
You're using a dark energy probe as a part-time exoplanet autopsy machine just to maximize efficiency.
Exactly.
And this downtime project resulted in a study published in the monthly notices of the Royal Astronomical Society that fundamentally benchmarks our understanding of rocky planets.
The insight was that a spectrograph doesn't care what it's pointing at.
Right, light is light.
DII was engineered with unprecedented sensitivity to capture the faint spectra of galaxies, which means it is uniquely overpowered for capturing the faint absorption lines of metal pollution on white dwarfs.
It was the perfect accidental tool for the job.
Exactly.
Well, let's dig into the actual autopsy data, because Paula Isconcerto's team sifted through the DI observations and identified 12 specific, highly metal-enriched white dwarfs.
Yes.
12 dead stars currently in the act of devouring shredded planets.
Right now.
So before we look at the specific elements, what is the grand goal of isolating these 12? Like, what is the core question they're trying to answer?
The core question is really about cosmic normality.
Meaning what?
Well, we know exactly what the Earth, Mars, and the asteroids in our solar system are made of.
Right.
But we have a sample size of exactly one solar system.
Ah.
We don't know if our specific recipe of rocks and metals is common across the galaxy, or if the Earth is some bizarre, rare anomaly.
Right. Maybe we're the weirdos.
Exactly. Paul Isconcerto notes that to understand this, we need a massive, statistically significant sample size of exoplanetary chemical compositions.
And since we obviously can't send a rover to a planet 500 light years away to scoop up dirt,
Sadly, no.
the only way to get that sample is to read the barcodes of the planets as they vaporize in a white dwarf's atmosphere.
Precisely.
Wow.
And the results from these 12 systems were striking.
What did they find?
Across the board, astronomers found between 3 and 10 distinct heavy elements polluting the atmospheres of these stars.
The elements they identified were oxygen, magnesium, silicon, calcium, and iron.
Yes.
Now, I look at that list and it doesn't sound very exotic.
No, it doesn't.
It sounds like a lot of ingredients for like a concrete foundation.
That's exactly why it is so profoundly exciting.
Really?
Yes, those aren't random trace elements. Those are the fundamental building blocks of rocky planets.
Oh,
In planetary science, we talk about planetary differentiation.
remind me what that is.
So when a rocky body forms, the heaviest elements, primarily iron, sink to the center to form a metallic core.
Like Earth's iron core.
Exactly. Then the lighter elements, silicon and magnesium and oxygen, they bind together to form silicate minerals, things like olivine and pyroxene.
That's the rock part.
Right. Those make up the vast bulk of planets' mantle and crust. And calcium is a key refractory element found in the earliest, most primitive stages of planet formation.
So the fact that we are seeing iron, silicon, magnesium, and oxygen raining down on these white dwarfs,
Yes.
it proves that the planetary bodies being destroyed had the exact same fundamental geology as Earth.
The verdict of the DI data is unequivocal. The debris mirrors the major rock-forming elements seen in our own solar system.
Wow.
In fact, their elemental abundance ratios closely resemble primitive meteorites.
Okay, when you say primitive meteorites, you mean things like chondrites,
Yes.
like the undisturbed leftover rubble from our own system's formation.
Yes, specifically CI chondrites.
Chondrites.
Right. These are meteorites that have never been melted or differentiated. They represent the pristine, totally unmixed chemical recipe of the solar nebula that birthed the Earth.
Oh, wow.
By observing those exact same ratios in the debris of destroyed exoplanets, it confirms that the mechanics and the chemistry of planet formation are universal.
So they happen everywhere.
Yes. The processes that built our world are operating continuously across the Milky Way.
Having the same ingredients in the pantry is a huge revelation.
It is.
But I want to go deeper into the data because the study didn't just stop at a broad overview of 12 stars.
No, they pushed it further.
Right. Out of those 12, the team found that 6 offered spectra that were exceptionally clean.
This is where we get into the granular power of spectroscopy.
Okay.
Because even with a machine as powerful as DSI, some spectra are going to be noisy.
Right.
Maybe the white dwarf is slightly further away, or it has a strong magnetic field causing something called the Zeeman effect.
Which does what?
It smears the spectral lines, making it really hard to get precise elemental abundances.
But for 6 of them, the signal-to-noise ratio was near perfect.
Yes.
The data was crystal clear.
And with those 6 clean spectra, the astronomers could move past simply listing the ingredients.
They could measure them.
They could measure the exact stoichiometric ratios of the elements. They could literally reconstruct the distinct types of planets or planetesimals that had been shredded.
Okay, the breakdown of those 6 is where this study goes from fascinating geology to basically hunting for the origins of life.
It really takes a turn, doesn't it?
It totally does. The analysis split the 6 clean spectra into 2 distinct categories.
Right.
4 of them pointed to completely dry rock-forming composition.
Yeah, the data for those 4 stars showed an abundance of iron, magnesium, and silicon. But importantly, the ratios indicated a total lack of volatile elements.
Volatile meaning things that evaporate easily.
Exactly. These were bodies that formed in the inner regions of their respective solar systems, where the intense heat of the young star prevented elements like water from condensing into ice.
So we're talking about barren, irradiated rocks, like analogs to the planet Mercury or just dry asteroids.
Highly refractory, totally dry material. But the other 2 spectra, they provided the massive twist.
The final 2 out of the 6 clean observations showed something fundamentally different in their chemistry.
They did.
Massive, distinct oxygen signatures.
Massive.
Let's slow down and look at the chemistry here. Because if I see a spike in oxygen in the data, my first instinct is to think, okay, the planet had an oxygen-rich atmosphere like Earth.
Sure, that's a natural assumption.
But we are talking about a pulverized planet dropping into a star. How do scientists know that an oxygen spike specifically means water rather than just, a bunch of oxygen gas?
It comes down to a concept called oxygen fugacity and basic stoichiometry.
Okay, unpack that for me.
So when a planet is shredded and falls into the white dwarf, its molecules are blasted apart into individual atoms.
Right, it's too hot for molecules.
Exactly. We can't see the water molecules themselves. We just see individual oxygen, iron, and silicon atoms. However, geochemists know exactly how these elements bind together in a solid rock.
Right, because oxygen is incredibly reactive.
Oh, extremely reactive.
It doesn't just sit there, it binds with the metals.
Exactly. In a dry rock, virtually all the oxygen is bound to silicon to form silicon dioxide, which is essentially quartz or sand.
Okay.
Or it's bound to iron and magnesium to form various oxides in the mantle. There is a strict mathematical limit to how much oxygen can be locked up in these dry minerals.
So the astronomers essentially do an audit.
An audit. I love that, yes.
They count all the silicon, magnesium, and iron atoms they see in the spectrum.
Right.
And they calculate exactly how much oxygen will be required to oxidize all of that metal into rock.
And when they did that audit for these two specific white dwarfs, the math didn't add up.
There was leftovers.
Exactly. There was a massive excess of oxygen. Way more oxygen than could possibly be explained by dry rock chemistry alone.
And since it couldn't have been bound to the rocks, it had to have been bound to something else before the planet was destroyed.
It had to be bound to a highly abundant volatile element that doesn't leave a heavy trace in the white dwarf's spectrum.
Hydrogen.
The only realistic candidate in planetary formation models is hydrogen. The excess oxygen was originally bound to hydrogen in the form of H2O.
Wow. So the excess oxygen signature is basically the ghost of ancient water.
The implication is undeniable. These two oxide-rich signatures originated from water-rich planetesimals.
Planetesimals being like early building blocks of planets.
Right, and these bodies must have formed beyond the snow line of their solar system.
There's no line?
At where it was cold enough for water ice to condense and get mixed in with the rock as the planetesimals accreted.
Paula Izquierdo's team noted something about this specific composition, right? Rocky material heavily enriched with water.
Yeah.
This isn't just an arbitrary ice cube in space. It perfectly mimics the theoretical models of the early Earth.
It is the exact analog.
That's incredible.
Earth itself formed inside our solar system's snow line, meaning it should have been bone dry.
Wait, really? Earth should be dry.
Yes. The leading consensus is that the early Earth acquired its oceans late in its formation.
How?
They were delivered by impacts from water-rich planetesimals and asteroids migrating in from the outer solar system.
So we are literally watching the delivery mechanism for oceans being shredded by a dead star.
Yes, we are.
Finding water-rich planetesimal debris is basically the holy grail for astronomers trying to figure out if habitable worlds are common.
Finding that 2 out of the 6 clean spectra point toward water-rich bodies is a stunning ratio.
2 out of 6, that's a third.
It suggests that the chemical prerequisites for oceans, and by extension, the potential chemistry for life, might be incredibly common around other stars.
Wow.
We are observing the raw ingredients of early Earth analogs being scattered across the galaxy.
The scale of what we are deducing here is just staggering.
It really is.
Think about it. We are looking at a spectral barcode of a dead star, captured by a machine that was built to map dark energy.
Right.
Only used because the weather in Arizona was too cloudy to see distant galaxies.
Yep.
And from that, we are mathematically proving the existence of ancient water on a destroyed planet hundreds of light years away.
It is a profound demonstration of how interconnected astrophysical disciplines have become. The universe doesn't silo its phenomena.
That's a great way to put it.
By adapting to the weather, this team unlocked a completely new utility for a major cosmological instrument.
So what does this all mean for the future of this research?
True.
Because we started with the premise that we had a sample size of 1 for a rocky planet composition. Paula Izquierdo's team has added 12 highly detailed autopsies to the record. Where does DSci go from here?
The big picture is that DSci has now been definitively proven as an unparalleled tracer for metal-rich white dwarfs. It works perfectly. This wasn't just a one-off experiment. It's a proof of concept. As DAI's primary 5-year mission continues, there will inevitably be more nights of poor atmospheric seeing.
More cloudy days in Arizona.
Exactly. And the team will continue to utilize this downtime.
They can just keep running the background program, capturing thousands of white dwarf spectra while they wait for the sky to clear for the galaxies.
Exactly. They're building a massive statistical database of exoplanetary geology.
A census.
Yes, a census. Every new spectrum we analyze adds another data point, unlocking the precise ratios of planetary formation across totally different stellar environments.
That's amazing.
We are moving from that sample size of 1 into a true galaxy-wide census of planetary chemistry. We will eventually know, statistically, exactly how common an Earth-like planet is.
If you have iron, silicon, and oxygen, you essentially have the recipe for Earth. But I guess this census will tell us if finding the recipe means the cake tastes the same, right?
I love that analogy. Exactly. It tells us if the cake bakes the same way everywhere else.
And every ruining planet falling into a white dwarf tells us a story about a solar system that might have looked a lot like ours.
It does.
Which, frankly, brings us back to the gravity of the hook we started with. Because we aren't just studying alien worlds.
No, we're not.
We are studying our own future.
This raises an important, deeply sobering question. We know the timeline for our own sun.
Right.
In about 5 billion years, it will exhaust its hydrogen fuel. It will swell into a red giant, vaporizing the inner planets, including Earth, before shedding its outer layers and collapsing into a white dwarf.
The mass loss will happen here.
The mass loss will happen here. The gravitational anchor of our solar system will weaken. Jupiter, Saturn, Uranus, and Neptune will migrate.
And when they migrate?
Their orbits will expand, and as they do, they will sweep through the asteroid belt, the Kuiper belt, and whatever remains of the inner solar system.
The cosmic blender turns on.
Exactly. The stellar billiards, the chaotic N-body scattering, will happen in our own backyard.
The icy, water-rich bodies of the outer solar system will be hurled inward.
Yes. They will cross the Roche limit of the white dwarf that used to be our sun.
Wow.
They will be sheared apart by tidal forces, pulverized into an accretion disk, and rained down onto the pristine surface, leaving brief, fleeting signatures of oxygen, magnesium, and iron.
So when we use DSI to look at these shredded, water-rich planetesimals falling into the fires of dead stars in the constellation Virgo, we aren't just doing geology. We are looking into a cosmic mirror at the inevitable, chaotic fate of our own home.
We really are.
We are watching a preview of our own solar system's remains being stretched, shattered, and consumed.
We are looking at the final act of a planetary system, captured in the light of its dying star.
That is just wild.
And perhaps billions of years from now, astronomers on a world we cannot yet imagine will point their own spectrographs at a faint white dwarf in the Milky Way.
Read the excess oxygen in the barcode.
Exactly. And wonder if there was ever water or life on the rocks falling into the fire.
That is a thought that will definitely stick with you the next time you look up at the night sky. You might find yourself wondering which of those quiet, twinkling point sources is currently hiding our solar system's identical twins.
And which ones are actively broadcasting their final moments.
Exactly, broadcasting the final moments of a story just like ours. Well, thanks for joining us for this deep dive into stellar pollution and shattered worlds. Until next time, keep looking up.